Okay, coming back to the class, we have already seen about the frictional resistance and wave making resistance. These are the major components of resistance, and these resistance are primarily confining to underwater portion of the ship. But above water portion also above the ship also is subject to resistance. So, now here the fluid is air, it is not water, whereas the density of air is about 1/800th of that of water. So, the importance is not so felt for the above water portion, that is the air resistance component, if the ship operates at low speed. If the ship operates the high speed, that is if you consider high speed category vessels, then the wind effect or air effect will be more, mainly the air effect will be more. So, here the difference between air and wind is air is the case where you consider still air and the ship is moving. So, that means you as good consider the flow of air in the opposite directions of that of the ship with the same velocity of the ship. So, that is what is considered. So, this component become important or considerable when you consider fast ships, one aspect, and another thing is when you consider the above water portion of the ship is high, like in the case of container ships, passenger ships, ro-ro ships, where the above water portion of the ship is high, whereas when it comes to tanker or bulk carriers, the above water portion is not so high, and also this tanker and bulk carriers operate at less speed. So, the speed of air is less, whereas the wind you consider, wind is coming from the nature, the natural wind, which may come from any direction. So, you do not have a control on that. So, but physically these both can be clubbed together, treated in the same way, air and wind resistance. So, that is what we look into next. So, the resistance that is experienced about same what I said, above water portion of the ship, it moves through the air, that is air resistance. It acts on the above water portion of the ship, it depends on the ship's speed, as I said, or area and shape of the structure. So, area means what is the exposed area to the direction of the wind, and also the shape, where it is having very streamlined shape or it is having a blunt shape. With a blunt shape, it will have more resistance, more air eddy formation, drag and all that will be more. So, these aspects you have to consider. And okay. So, then coming to the wind resistance, the wind resistance depends on the wind speed, it is coming from the nature and its relative direction, whether it is coming ahead opposite to the ship or it is coming from behind or coming from the side or it is oblique. So, depends on the direction of the wind, the effect on the ship resistance changes. So, it can be convenient to take air and resistance together, as I said, both air and it is a air media. So, you usually can be considered together. Air resistance is usually determined in wind tunnel test. How do you determine? Because ship, you know that above water portion got many types of structures, mast is there, engines are there, winches are there, superstructure, accommodation spaces, there are many items coming on that. Then above water portion, hull part of the ship, above water portion, all these come. So, the shapes are different and orientation is different. There may be this, there is a mast behind another mast. So, when you consider air, there is the effects called the consolidation effect, and I think the other one is the basically the subsiding effect. Consolidation increases the chances of increases the wind effect. Other one is called the shielding effect. So, one is behind the other, the first one get the maximum load, one is behind the other will get less effect if it is close by. So, that is called the shielding effect. The second one is shielded by the first structure, or if they are together side by side in the direction, then there will be a build up of the constriction, the flow velocity increases, which is called the consolidation effect. So, depending on the orientation of the structure, depending on the shape of the structure, depending on the size and all this matters in the determination of air resistance. So, it is not easy to analyze it. So, what people do is they usually perform a test in the wind tunnel. You put a model of the structure, you flow the air through the wind tunnel at different velocity, you find out what is the drag coefficient, what is the force coming on that. So, this is how you estimate. So, these coefficients for different typical section shapes and structures are available in literature based on the experimental studies carried out by different research groups using the wind tunnel. So, what you can do is you can borrow these values or these coefficients from the literature and use it in your calculation if you know the shape of the structure. Wind action causes reduction in speed, that is when a wind is acting, that it is coming from nature, it causes a reduction in speed, which is if it is opposing, the ship is moving forward, wind is opposing it, then the speed reduces because it is blocking that, there is an blockage due to the wind action. Then a heeling of the ship, when the wind acts from the side, if your wind is acting from the side, ship heels to one side, is not it. So, when you consider action of wind, I just consider you have a superstructure accommodation and everything coming here. You may have mast, maybe crane here, depending on the ship hold and all that. This is underwater portion, this is the water level. So, this area is now exposed to air. You have this area, this area exposed to air. So, when the wind acts in this direction, if you look to the other view, suppose this is a sectional view of that shape or from the end view, this is a water level. So, you have this water level, then you have the structures, superstructures and all that. So, okay, this is a concern. If the wind acts from this direction, that means there is a chance of the ship getting heeled to one side. When the ship heeled to one side, the hydrodynamic performance of the ship deteriorates. That means the resistance of the ship increases than when you compare it with a zero heel condition. The ship will have the least resistance when it is having a zero heel. So, when it is subject to a heel, the resistance increases, that is what it means. So, that is what it means, that the heeling of the ship which causes a reduction in speed, that is the resistance increases speed. Then the third one, the ship course change, that is if you consider from the plan view, if the wind acts maybe in this direction. So, what happens is that it induces a moment in this direction and then the ship will turn this way. The ship may turn, isn't it? The ship will turn. So, that means there is a drift angle introduced by this action. So, due to the action of the wind, the ship may drift to one side, it generates a drift angle. So, when ship generates a drift angle, then the resistance increases drastically. Instead of going straight, which is the least resistance orientation of the ship, and if the ship moves and then it moves, then tilt and moves, then the resistance increases. So, due to the action of the wind, it will be a blocking effect which reduces speed. Then there is a heeling effect, can be a heeling effect which again reduces the speed or increases the resistance. And the third thing, it says that the ship changes the course, that is it will have drift angle which increases the resistance drastically. So, these are the wind effects. The last two effects, that is the heeling and course, increases resistance and term as a wind induced resistance, that is actually it is not wind directly blocking it, because of the action of the wind the orientation of the ship changes and subsequently the resistance increases, then the speed comes down. So, that is why it is called wind induced resistance. Okay. Now, how do you estimate this, the wind resistance? So, what you have is you have all these coefficients known from, as I said, from the wind tunnel test. You consider the wind force results in axial force if it is in the x direction, there is a component, then transverse force y direction, there can be a component, and it gives a moment. So, this all things are considered in the horizontal plane. You have the x force, y force, and moment, your moment. So, these are the force components in the horizontal plane. So, if you want to find out the axial force coefficient is represented by the axial force divided by half rho a V r square into a v t. So, rho a is a air density, V r is the wind velocity, relative wind velocity, that is in relation to the ship speed. What is the relative wind velocity? And a v t is a projected area of the ship above the waterline, that is a transverse area. So, you are considering x direction. So, what you consider here is, that is the wind is blowing in this direction, that is the wind velocity. So, you have take the projected area of the above water portion in a plane normal to this. So, in the transverse plane. So, that means this is a plane. So, this is the area now subject to wind. So, this AVT is representing this area, AVT represents this area. So, that is a projected front area, projecting front area of the ship above the waterline. So, that is a transverse plane. So, that is the AVT. Now, you consider transverse wind coefficient, that is wind blowing in the transverse direction, that is when it blows across the ship, the beam direction. So, you consider the y force divided by half rho a and v r square and a v l. Here the projected areas, you usually take the plane, the area in projected to a plane normal to the wind velocity direction. So, that is what you can say, a v l. So, here that is how the C y or the transverse wind coefficient is. So, if this is the case, you consider this is the one, this is the area, now the wind is acting in this direction. So, this is the area which gives the a v l. So, this area gives a v l, and your coefficient, your wind moment coefficient is given by the total moment divided by half rho a v r square into a v l into L O A, which is representing a moment quantity. So, this is another. So, these coefficients are obtained using this relation. So, what you have is, in literature you will be able to get, from literature you will be able to get all these coefficients C x, C y and C n. So, these things are available in the literature based on the wind tunnel test. So, this coefficient literature is available. So, you borrow that appropriate value depending on the shape of the structure, size or shape and form of the structure, you get these quantities from the literature. Yeah, that is that values coefficient C x, C y and C n are usually obtained from the experiments in wind tunnel, or you can perform your, if you have wind tunnel facility, you can perform it, test and get the coefficient. These coefficients depend on number, that is number of structures, the relative size and form of the superstructure. So, superstructure usually is referring to, that is a structure coming about the main deck of the ship. So, you have to know how many numbers of structures are there, what is the size, relative size of the structure, and what is the form of the structure. Is it a square cylinder or square shape, or it is having a smooth shape, maybe circular cylinder, or maybe what is the shape for that. Then type and number of equipment on the weather deck, that is on the top deck you will have number of equipments for various operations, including the crane operation, anchor operation, mooring line operation, there are marine machinery on the deck. So, these equipments also will have a effect from the wind. So, you find out that also. So, based on all these categories, the total, generally the vessels are classified into, with reference to wind force, with classified into 3 types, 3 groups, group 1, group 2 and group 3. Group 1 is a general cargo ship, bulk carriers, tankers, fishing boats and tugs. Generally their freeboard is less and above water portion also less. So, these all come under the category of group 1. Category 2 is container ship. You might have seen container ship pictures with lot of containers stacked on deck. So, the wind blockage is very high for container ships, and it is a bad for the ship, and you already know a container ship is the stability of the ship is at stake. It is because of the top loading, and with the wind effect it is going to be worse. So, whenever you design the ship, you have to consider wind effect also to analyze the ship stability. So, that is another class, group 2 container ship. The third group is a passenger ships and passenger ferries. So, that is another class. So, these are the general classification of the ship, because based on which these coefficients are prescribed. So, the force coefficient values, what are Cx, Cy and Cn for different groups are as we see below. See, these values changes depending on the loading condition of the ship. The fully, normally you consider full loaded condition, but when the ship is not fully loaded, you know, the ship usually has conventional ships. They have conventional cargo ships. They have 4 operating conditions. One is a fully loaded departure condition, fully loaded arrival condition, fully loaded ballast departure condition and ballast arrival. These are the 4 operating conditions normally considered in the design stage. So, at fully loaded departure condition means that is all the stores are full, that is fuel oil and stores are full and cargo is full. So, the vessel is floating at the design load water line, but during the course of its operation, when it is moving from one port to another, it consumes lot of oil and also the provision other consumables. So, the displacement reduces marginally. So, when it reaches the other side, other port, we expect the stores or consumables balance may be around 10 to 20%, that is 80%, 80 to 90% consumed. That is why it is called a fully loaded arrival condition, that is the difference. But when it is coming back, the ship may not have cargo, so it has to come the cargo hold empty. So, it has to maintain the water depth and everything. For the proper immersion, it go for ballast. So, what it does is it replenish the stores from the port which has arrived. That means, stores become full 100%, but it is in a ballast condition. Ballast condition normally you say it is around 35-40% of the displacement of the ship. So, stores full, then there is a ballast departure condition. When it comes to the other port, during its course of journey, it has consumed the stores, maybe again 80 to 90% consumed. So, again the displacement changes, resistance changes, underwater portion different, above water portion different. So, that is why these are considered separately. So, that is what it says, that these coefficient values are usually taken for fully loaded condition. If it is in a ballast condition, these coefficients Cx, Cy and Cn need some adjustments. So, what it says that Cx is 5 to 10% less than the loaded condition. Why it is less? 5 to 10% less than the load condition. Cx is not the total wind load in x direction, it is the Cx, the coefficient is coming less in ballast condition. That is, the ballast condition, this quantity is less compared to the fully loaded condition, because the portion which has emerged is more streamlined, is not it? The portion which has come out, the ship, when it is the ballast condition, the ship hull came out. So, but the portion which has come out is more streamlined. So, the air effect Cx in x direction, because of the streamlining, the wind effect will be less for that exposed portion. That is why the Cx value comes down, but the total load will be high because the area is increased. So, when you consider the area, total will be more. Cy is going to be more because more exposed area and blockage is more along the length. So, that is not going to help, the streamlining is not there in that longitudinal plane. So, that is 5 to 10% more, and naturally because of that the CN also goes up, it goes up 10 to 70%, that is very high. So, these are the things which occur. So, you have to make a correction for these values when you consider the ship operating in ballast condition. So, usually you design it for the fully loaded condition, but the ship also operates in ballast condition. In such cases the wind load need to be estimated with this one, but the thing here is the total resistance reduces in the ballast condition, because the displacement has come down, the wetted surface has come down, resistance comes down. So, even if the wind component goes up in some cases, the total resistance will be less than that in the case of the fully loaded condition. So, the axial wind force coefficient values in the group 1 ships, which you have seen that cargo ships generally, general cargo, bulk carrier, tankers and all that. So, this is the Cx value. So, here you can see it is plotted against the direction of wind. So, if the wind operates, it is positive and negative, you can see that if 0 to 90, 0 to 90 it is negative, 0 to 90 means what? Wind acting in which direction? The 0 to the direction of wind, you know that it acts in. So, when you consider the ship here, the ship is moving in this direction. If a wind also in this direction, it is 0 degree. The wind acts in this direction, it is 180 degree. If the wind acts in this direction, it is 90 degree. Okay. So, that is so that means that 0 to 90 means wind is in the same direction of that of the ship. Same direction means actually it is following the ship. That means it is giving a pushing effect for the ship. So, that means Cx is negative. You can see that this region Cx is negative, but when it from 90 to 180 degree is going the other way, going to the forward side and opposing the motion of the ship. So, Cx value you can see that it is going to be positive. At 90 degrees you can see it is 0, because it is not going to influence any x component force when the wind acts normal to the ship. So, it is not going to, so that is how. So, this is a characteristic representation, the value of which you get from the wind tunnel experiment. You look to the transverse force coefficient, group 1 ships. This is a diagram, you can see that Cy against the wind. So, the transverse coefficient, that is in the beam wind condition. So, the maximum effect comes as 90 degree, is not it? The maximum effect will be at 90 degree, whereas at 0 and 180 degree it will be 0, there is no effect, is not it? Suppose the wind is acting in along the length of the ship, it is not going to induce a transverse force. So, that is why it is 0. So, whether it acts in the 0 degree following that ship, or it acts at 180 degree opposing the ship, its effect on the transverse direction is 0. The maximum effect comes only when wind acts at 90 degrees. So, that is how the curves, all the curves are shown. So, here you can see the effect, see very large tanks, the freeboard is less, bulk carriers. So, the very large tank, the freeboard, so that means the effect, wind effect is less, that is the lowest curve. Tanker is having higher higher freeboard, and so when it comes to freeboard classification, you come to know that the tanker is, I think, type A ship, and other ships come type B, and bulk carriers are type B60 ship, I think. So, that is a variation. So, here you can see that this is the bulk carrier, and here the freeboard is higher compared to tanker. So, you have more effect. When it comes to general cargo ship and fishing boats and all that, it is going to be higher and the effect is small. So, that is you can see the Cy value, how it varies for different types of ships. That is for the group 1. So, we will have similar curve for the group 2 and group 3. Group 1 ships, you know, it is a general cargo ship, bulk carrier, container ship, fishing vessels, all these categories. So, again the Cn values for group 1 ship, you can see that this is the trend. So, here the effect is more where the concentration of the area is. So, that is why it is put deck house. Deck house is the basically a superstructure accommodation space which comes. So, that means deck house aft or forward. So, here you can see this is a deck house, this is the accommodation area, this is the main deck, this is the main deck or weather deck called. So, any structure which come above this deck is called superstructure. Here this maybe it is a superstructure or deck house, this is the aft of the ship, and sometimes you get in the middle or sometimes you get the forward side. So, depending on that position there will be a change in the moment, the wind action moment. So, that is what is accounted here. You can see the deck house forward, this is the curve, deck house amidship, this is the curve, or I think aft may be one of this curve, and then you have for the other generally very large tankers and bulk carriers and all that. So, this gives an indication, one with respect to type of ship, it gives CN value with respect to type of ship, it gives CN value with respect to location of the deck house or superstructure, and also it gives the CN value with respect to the direction of the wind. So, you can see that 0 to 1. So, you have to identify which direction the wind is acting and what is the type, what are these things. You pick out the value for the respective, pick out the CN value for the from the respective curve, and that will be used in the expression, isn't it. Once you get this Cx and all these values, you put it here. Cx is known, Cy is known, Cn known. So, you know all these parameters in the denominator, air density, velocity of wind is known, area is known. So, from which you get x, y and n. So, you get what is the force. So, that what I have discussed are for the group 1 ships. You can see that Cx for group 1, Cx for Cy for group 1 and Cn for group 1. Now, you consider the same thing for group 2 ships. Group 2 ship is container ship, you recall that what we defines the container ship. So, here the variation you can see the trend is same, but the values differ due to the higher freeboard and deck positions and all that. So, you can see these values. If you have a one tier, that is you are stacking only one tier of container above deck, or if you have 3 tiers of containers above deck. So, if there is a variation, you just look at it, you can see that difference how it is changing here. So, this blue line shows there is no container on deck, but still the container freeboard is high, container ship freeboard is high, that will have a effect on these values. Same container ship group 2, what is the effect you can say with the one tier, 3 tiers and no container on deck, no containers put on deck. So, this obviously, so you can see that 3 tier will have more effect, 1 tier will less, and the least effect is with no containers on deck. So, you have less exposure and less, and containers are usually block, it is a rectangular block. So, naturally the wind effect will be more because of the sharp corners and edges and all that. So, this is again container ship group 2, the CN values here. So, trend remains same, only the values you see that it is different, and depending on the number of tiers used and number whether it is used or not. So, now same thing for group 3 ship. Group 3 ship we have seen is a passenger ship or passenger ferries, and this is a variation here. You can see there is almost flat here and then it goes like that. So, maybe wind acting from maybe 60 degree to 120 degree, it is almost the same effect. Same thing Cy, you can see again the Cy values remain same constant over this range, that is 60 degree to 120 degree because of the shape, basically that is the shape of the vessel and freeboard. So, this is a trend for the this moment coefficient, yaw moment coefficient. So, what I mean is you get all these coefficients, all these are available in literature which has been evolved through the experiments, and get these values, use it in the expression, get the wind force, and from the wind force you take the component opposing the ship motion. So, from that you will be able to find out what is the resistance, isn't it? The ship is moving forward, the wind may be coming in this direction or maybe this direction. You take the component x component of that and then you put it along with that, and then you find out that is the resistance offered. That is one aspect. Second aspect is, we have seen before, what are the aspects? Only the speed reduction due to resistance, other two are heel and course change or the drift angle. So, if the wind is coming, if the y force, you will give you information about the heeling, isn't it? If you have y force, you know where it is acting and you know what is the heeling moment due to wind, and you will be able to find out what is the heel angle due to the action of wind, which usually taken as from the transverse component. So, due to the heel, then you will be able to judge what is the increase in resistance due to the heeled orientation of the ship. And the third one, that is a moment, yaw moment. When the yaw moment you know how much the ship is going to drift. So, in that drift position, what is going to be the wind resistance. So, you have to give all these three informations help in finding you the effect due to various aspects. So, here the preliminary design stage of a ship, when not knowing the windage of the ship designs, because in the preliminary stages you do not know what is the superstructure, what is the exact shape, form and everything is not known. So, you do not have an idea about the actual superstructure size, superstructure shape and orientation and everything you do not know. So, what you do is you go by some standard empirical relations, which again observed through studies. So, use that values. So, CAA is for the still air resistance coefficient, it is not due to the wind, it is due to the air resistance. So, this CAA represents that, and so it is given by, you use 1A, why you have used 2A here? Because already you have used one CA, CA is used in resistance, CA represents the ship model correlation allowance, CA is already used for that. So, that is why you put CAA for the air resistance. The ship model correlation allowance is due to account for the, we will see it later, to the change in roughness between the model and ship. So, that is accounted by the ship model correlation allowance. So, here the whole thing, even though you talk about air resistance, these parameters are given for the underwater thing, that is you have water density, ship speed remains same, and also the wetter surface, these are the quantities used here. So, this is based on just, because these quantities are better known even at the preliminary stages. You know what is the surface area, at least through empirical relations, if you know the dimensions and coefficients, you can find out the wetter surface area from the design, but you are not clear about the above water portion. So, that is why these parameters are selected for the non-dimensionalization. The force coefficient values are given like this, that is, if it is a general cargo ship, you just give an allowance. So, you get frictional resistance CF coefficient, you have wave making or residual resistance coefficient CR. So, you are adding that from the model test. Now, you put another allowance CAA is equal to 0.1 into 10 power minus 3 for the air resistance. So, you just add it. If it is a general cargo ship, if it is a bulk carrier, this is the value, tanker this is the value, you can see that the change in value also. If it is a VLC is very large crude oil carrier, then this is the value, you can see the value is less. Fishing boats, the value has gone up, and container ship value is not say, for there is no container on deck, value is only small, but if the containers on deck, the value has gone up. Passengers, so this is the value, ferries. So, these are the values you select and just put it along with the other resistance coefficients to get the total resistance coefficient, which will help you in predicting the getting the total coefficient and predicting the prototype resistance, because when you perform the model test in a lab condition, you are not measuring the wind resistance or air resistance. So, this completes almost all the components of resistance. There are some other small components and all that, which are usually like wave breaking resistance, then small components also present. These are the major components, that is the frictional resistance, wave making resistance and air resistance. Air resistance comparatively very small compared to the other two components. So, once you get this, you can find out, then you have other elements as we see later, and which put along with that you find out the total resistance of the. So, now we move on to the next topic, this is a dimensional analysis. You know, the dimensional analysis are carried out on equations and physical quantities. Basically, to predict, we give non-dimensional parameters which can be applied to geometrically similar body at different scales. So, basically it is done to predict the prototype resistance value or parameters, hydrodynamic parameters from the model test. So, you can see here every equation which expresses a physical relation must be dimensionally homogeneous. Isn't it? When you write an equation, you are writing an equation of motion or any equation, all the terms should have the same dimension. If it is a linear equation of motion, you will get all the terms in newtons unit. If it is a rotational motion equation, then all the terms will be moment, that is Newton meter. So, similarly any equation when you write, even other physical problems, you have to see that when you write the equation, all the terms, that is the homogeneity of the dimension should be there in the equation. So, when you represent the fundamental, when you represent any term, any physical term, it can be derived or presented from the basic quantities in mechanics, which is mass, length and time. So, if you know m, l and t, you can derive other quantities, the units of other quantities. So, applying dimensional, now we are discussing ship resistance. You know, ship resistance depends on density of fluid, water or air, depends on the speed. We have already seen the resistance, frictional resistance proportional to V power 1.825 and residual resistance proportional to V power 6. So, it is depending on V, depends on L. We have seen that it depends on Reynolds number, it depends on Froude number. So, we know that it is L is a parameter on all these things, it depends on the length, it depends on the viscosity, the friction mainly, it depends on the viscosity, depends on G, gravitation, acceleration due to gravitation, because that is the one which determines size of the wave. So, if there is less gravity, higher will be the size of the wave, and so G is a factor there, and the pressure, which again depends, determines the pressure related resistance. You know, wave making resistance is pressure related, viscous pressure resistance is again pressure resistance. So, all these type of components will have an influence on the pressure. So, since the resistance are depends on, okay, that is what I said, it depends on density, speed and everything, this we have just mentioned, fluid pressure. Resistance is a force, and hence we can say mass into acceleration, mass into L by T square, that is a resistance of force. Rho is a density, is mass per L cube, meter, so kilogram per meter cube, or this is mass per L cube, that is a representation of that. So, when you come to viscous force, what is you just find out what is the unit of mu, what is the unit of dynamic viscosity. We know the relation from the Newtonian relation, tau is equal to mu into dou u by dou y, isn't it, or du by dy, that is the relation given for Newtonian. So, that into area, that gives the viscous force. Tau is a shear force. So, if the body is moving, there is a shearing effect, shear stress is proportional to velocity gradient for any Newtonian fluid, where water is a Newtonian fluid. So, if you integrate the tau is the shear stress. So, if you integrate the shear stress, then you get the shear force over the better surface, isn't it. So, that is what is done, the shear force is given, F is equal to mu into A into the velocity gradient. So, this is a physical relation. Now, using this physical relation, how you derive the unit for mu? Using the fundamental units of mechanics, that is mass, length and time. So, here you can see that same F is equal to mass into acceleration m into L by T square, that is equal to mu, you do not know what is the unit, area is L square, u is L by T, y is L. So, now you simplify it. So, you get mu into L square by T. So, that means you get mu is equal to m by L T. That means mu is the unit of mu is, what is it, kilogram per meter per second, is not it. So, that is the unit of dynamic viscosity. That is how you derive the units, coming from the basic equation you derive the unit. So, P is a pressure which is force per unit area, and force is m into L by T square divided by area L square, and that is equal to m by L T square. So, that is the unit. So, that means kilogram divided by, you can just see that if you work it out, it will finally work out to be Newton per meter square, it will come. So, from the resistance expression what you have put here, from this relation I just put, I can write the same dimensional thing, m by L T is equal to, I put rho raised to a. So, rho is m by L cube and v raised to b, v is L by T raised to b, then length as it, then m by L T, this is the viscosity which you have derived now, and L by T square, that is a g, and the final one is the pressure, that also we derived now. So, we derived this just now and get back to the resistance relation, and we said, see that this is the relation normally you put. So, now you know, you just compare the coefficients on either side, m, if you say m is equal to 1 power a, m is equal to a here. So, this is a, m d, d is here, m f. So, a plus d plus f is equal to 1, you are comparing the power on either side of the equation. Similarly, for t, t is equal to okay, we will go by L, L is equal to 1. So, that is a 1 here, L raised to b, L raised to minus 3a, this is okay, this is minus 3a, L raised to b, then L raised to c, c here, then you have L here minus d, L here e, then L denominator minus f. So, this is equal to 1. Similarly, you have the expression for the, from comparing the power of t, that is a t is equal to 2. If you consider here t raised to here it is minus b, okay, it is all taken denominator negative, okay, 2, and here is b, and here it is d, and here is 2e, and here is 2f. So, that is what you get this relation. So, you have how many unknowns? 6, 1, 2, 3, 4, 5, 6, but only 3 equations. So, what do you see? You rearrange it and you put in this form, a b c and others in terms of a b c in terms of d e and f. So, now get back to say this relation, resistance equation. You can write resistance proportional rho into v square into L square into a function of these parameters. You can, this is only just rearranging that. So, here you have, it is a function of rho into v into L by mu, that is mu by rho is equal to nu, it is a dynamic viscosity by density is equal to kinematic viscosity. So, V L by nu is representing what? It is a Reynolds number, and here you have G L by V square or V square by G L and raised to minus E. So, which is representing the Froude number. So, here you have P by rho V square, which represents the Euler's number. So, you have all these things, all these parameters here. I think we discussed this before, and so what it means that resistance depends on Reynolds number, Froude number and Euler's number. So, that what means all the exponents of the bracket are non-dimensional. If you see that these are non-dimensional quantities, and the function f is all this. If you find this from experiment, you can evaluate the resistance. So, R is now proportional to, you can just using that previous relation, this relations over here, you write in this form over here, and finally you write R by half rho SV square is equal to function of these 3 numbers. So, if all the parameters on the right hand side, these parameters have the same value for 2 geometrically similar, but different size bodies, that is you are just indicating it is one model and the other one is a actual ship. So, if these quantities can be or remain same, then this quantity also remains same, that is what means. So, that this is a non-dimensional resistance or it is a resistance coefficient. So, resistance coefficient will be same provided these parameters also remain same for model and prototype. So, we will see subsequently whether this is possible. So, the size and then the flow, if that is the case, the flow pattern will be similar around the model and ship, and the value of this value also will be same, that is what is saying. If these values are same for model and ship, the flow pattern also will be same, and subsequently this value also remains. That is a resistance coefficient also remains same for ship and model. The equation shows that the total resistance of a ship depends on different quantities involved. These are associated with this. Okay, we have already discussed this. It depends on this. Considering inviscid fluid, if you consider no viscosity, that means this term is not considered. So, Reynolds number is not there, and neglecting the last parameter, you see that if you do not consider this, then the resistance will be depending only on this parameter, that is a Froude number. So, if you consider an inviscid fluid and this pressure variation is not considered, we see later how it is going to change it. So, then the resistance will depend only on the Froude number. So, if the fluid is inviscid, you will not have frictional resistance. So, but you will have the wave making resistance. So, if that is the case, if you satisfy this only the Froude number alone, you will be able to predict only the wave making resistance or in general residuary resistance. So, that is what it is concluding. So, the parameter GL by V square represent the wave making or residuary resistance can be considered. So, the resistance component will be the resistance if the Froude number is only satisfied, then the resistance which you can predict from the model is only the frictional resistance, or if you can satisfy the Reynolds number, you can predict the frictional component also. So, the residuary resistance coefficient CR is now put as residuary resistance R value divided by half rho SV square. This is a representation which depends on Froude number, that is what we discussed. If you satisfy only the Froude number, what you get is only the residuary resistance, and if you non-dimensionalize this, you get the CR, that is a residuary resistance coefficient. Comparing the residuary resistance of ship and its model, we say CRS, that of the ship is given by this quantity, that is residuary resistance of the ship divided by half rho S, that is the seawater density, that is the SS, the better surface area of the ship, and this is should be Vs, not nu s. Vs is the ship velocity, and that for the model you use the model parameters. RRM is the residual resistance measured for the from the model divided by half rho m. M is the freshwater density, that is the lab condition. Sm is the surface area of the model, and Vm is the model speed. So, from these relations, if you take, you find that since it is satisfying this one, CRS is equal to CR. So, that is what it infer when you satisfy this one. So, when you take the ratio of these two quantities, you see that assuming the density both cases being water same, you get this relation, that is RRS is equal to this quantity, and yeah, I think we will continue the next class.